Think about everything you do on your computer, playing games, high-end graphics, transferring huge files to those super fast SSDs, even just connecting to Wi-Fi. What's the invisible link? The thing making all that high-speed stuff possible.
Right. It's PCI Express or PCIe. And yeah, it's so fundamental, so deeply embedded in, well, pretty much all modern computing that we just take it for granted.
Absolutely. It's like the backbone, isn't it? The pathway letting all the parts inside your computer talk to each other and critically talk to the CPU.
Exactly. The central nervous system, you could say.
Yeah.
Connecting the CPU, the motherboard, to peripherals, graphics cards, SSDs, network adapters, everything.
And that's exactly what we're diving into today. We've pulled together, technical articles, industry specs, the real details to unpack the fundamentals of PCIe.
Yeah, our goal is to really understand how it works, how it's evolved, and get a solid handle on how software, especially those crucial drivers, makes the hardware tick.
So our mission for you, the listener, is to cut through that complexity.
Right. We want you to come away with a clear foundational understanding of this super important technology, appreciate why it matters, grasp the basics of how software interacts with it. Without needing an engineering degree. Consider this your shortcut, your express lane to understanding PCIe.
Exactly.
Okay, let's unpack this then. What exactly is PCIe? In simple terms.
Well, in essence, it's the standard for high-speed serial connections inside almost every modern computer. It connects the CPU and motherboard to all those key peripherals we mentioned. Graphics cards, SSDs, network adapters, other expansion cards, you name it.
And it replaced older ways of doing this, right? This isn't the first attempt.
No, definitely not. It came along to replace older parallel buses, things like PCI, PCIX, AGP. The big change, the fundamental shift, was to what's called a switched fabric architecture.
Switched fabric? Okay.
Yeah, instead of one shared road where everyone competed for bandwidth, PCIe gives each device its own dedicated point-to-point serial connection. Okay, so like going from a single congested lane to a multi-lane highway with dedicated on-ramps for everyone.
That's a great analogy, exactly. Everyone gets their own direct route.
Sounds much more efficient. What are the key benefits of that?
Oh, they're significant. First off, much higher throughput. Way more data can move.
Because it's dedicated.
Right. No bottlenecks from sharing. It also allows for full duplex communication data sending and receiving at the same time on the same link without interference.
Okay.
And because it's serial, not parallel, you need fewer physical pins. That means smaller connectors, smaller footprints on the board. Plus, it scales much better as speeds increase, and it has built-in error detection AER, advanced error reporting, which makes systems more reliable.
Okay, so each device gets its own lane, like you said, but then you see these terms like by 1 by 16. What do those X numbers mean?
Right, those X numbers tell you how many PCIe lanes are assigned to that specific slot or device. Common ones are by 1, by 2, by 4, by 8, and yeah, by 16, which you see for high-end graphics cards. The key thing is, the total bandwidth, the data capacity, scales pretty much directly with the number of lanes. And by 2 link has roughly double the bandwidth of an by 1 link from the same generation, and by 4 double that again, and so on.
Can you give some real-world examples? Where would you typically see in by 1 versus in by 16?
Sure. A simple Wi-Fi card or maybe a Bluetooth adapter might just use a single by 1 lane. That's plenty for what it needs to do.
Right, not a huge amount of data.
Exactly. But a fast NVMe SSD, that might use an by 4 connection to get those really high read-write speeds.
Okay.
And then your powerful gaming graphics card typically needs that full by 16 connection to handle the massive amounts of data for rendering complex scenes smoothly.
So it's about matching the device's needs to the number of lanes. And you mentioned the scalability makes PCIe very versatile.
Absolutely. Being able to scale the bandwidth, this is why PCIe works everywhere, from tiny low-power embedded systems all the way up to massive servers used for AI and machine learning, and, of course, in your desktop PC. And what's interesting, especially for software developers, is that the basic way communication happens over PCIe stays consistent, whether it's in by 1 link or in by 16 link. That consistency helps simplify driver development.
Now, PCIe isn't static, right? We keep hearing about new generations, Gen 3, Gen 4, Gen 5, Gen 6 is coming. What's the big improvement with each new version?
Yeah, it's constantly evolving. The main driver, pardon the pun, is the relentless demand for more bandwidth. So roughly every few years, a new generation comes out, and the headline is usually that it doubles the data transfer rate per lane compared to the previous one.
Doubles it. Wow.
Pretty much, yeah. And what's really clever is they've managed to do this while maintaining backward compatibility.
Ah, that's huge. So a new card can work in an older slot.
Generally, yes. You plug a new PCIe 4.0 card into a PCIe 3.0 slot, and it'll typically just run at the PCIe 3.0 speed. It makes upgrades much easier.
That's definitely good news. Our sources had a table summarizing these speeds. Can you walk us through some key numbers? How fast have things gotten?
Sure, let's look at the raw speed per lane. PCIe 1.0 back in 2003 used something called 8B10B encoding. It ran at 2.5 gigatransfers per second, GTs. That gave about maybe 0.25 gigabytes per second, GBs per lane. For by 16, that's around 4 gigabs total.
Okay.
PCI 2.0 in 2007 doubled that to 5 GTs per lane. Then PCI 3.0 in 2010 hit 8 GTs, but crucially, it switched to a more efficient encoding 128B, 130B.
More efficient. What does that mean?
It means less overhead. Think of the encoding as the packaging around the data. The 128B, 130B scheme has much less wasted space in the packaging compared to 8B10B. So the 8 GT's transfer rate translated almost directly to usable data throughput around 0.985 GB per lane, or nearly 16 GBs for an by 16 link.
Ah, I see. So from Gen 3 onwards, the GT's numbers are a pretty good indicator of the actual GB's data rate you get.
Pretty much, yeah. They're very close. Then PCIe 4.0 in 2017 doubled it again to 16 GTs per lane. PCI 5.0 in 2019 hit 32 GTs, and the latest, PCI 6.0, finalized in 2022, pushes it to 64 GTs and uses a new signaling method called PM4.
Wow. So for an by 16 slot with PCI 5.0, what kind of throughput are we talking?
For PCIe 5.0 by 16, you're looking at roughly 63 gigabs in each direction simultaneously. So like 126 gigabs total bidirectional bandwidth.
That's incredible.
And PCIe 6.0 aims to double that again to around 128 gigabs each way for by 16. It's this massive bandwidth that lets the newest SSDs and GPUs really stretch their legs.
But pushing speeds that high?
Yeah.
It can't be easy, right? Are there engineering challenges?
Oh, absolutely. It's not just about turning up the clock speed. At these incredibly high frequencies, sending the electrical signals reliably becomes really tough.
Right.
You run into major signal integrity problems.
Like what?
Things like insertion loss, the signal gets weaker as it travels down the wire, and crosstalk signals on nearby wires interfering with each other. It's like trying to whisper clearly across a very long, noisy room.
Okay.
So engineers have to use really sophisticated techniques called equalization, like CTLE and DFE. These basically clean up and reshape the signal at the receiving end to make sure the data gets through correctly.
Like digital noise canceling for the data signal.
Sort of, yeah. And they often need specialized materials for the circuit boards, materials that handle high frequencies better.
So even though a driver developer isn't messing with the electronics directly, these physical limits could cause issues that look like software problems.
Exactly. A driver might see weird errors or performance drops, and the root cause could actually be marginal signal integrity on the physical link. Understanding that the hardware has these limits is important context for developers.
Let's circle back to the lanes. You said each lane is full duplex. What does that mean physically? How is it wired?
Right, so a single PCIe lane isn't just one wire. It's actually two pairs of wires using what's called differential signaling.
Two pairs.
Yeah. One pair transmits data from the device to the host system, and the other pair transmits data from the host back to the device. So even a basic by one link has 4 wires total.
Ah, okay. Dedicated send and receive paths.
Exactly. That's what enables that simultaneous bidirectional full duplex communication for each lane.
And when we see in by 4 or by 16 slot, it literally has 4 16 sets of these transmit-receive pairs.
Precisely. The X number directly tells you how many of these full duplex lane connections are present. While I1, by 2, by 4, by 8, and by 16 are the most common, the spec does technically allow for by 12 and even by 32 links, but you rarely see those in practice.
And you mentioned bandwidth scales linearly. Can you give a quick example with, say, PCIe 5.0 numbers?
Sure. With PCI 5.0, a single by one lane gives you about 4 gigabits of bidirectional throughput. So a by 4 link offers around 16 gigabits total. By 8 gives you roughly 32 gigabits, and the full by 16 hits that impressive roughly 128 gigabits bidirectional figure. Simple multiplication.
You also said the number of lanes used gets negotiated automatically. How does that work? Why is that useful?
Yeah, during startup, what's called link training, The hardware on both ends of the connection, like the motherboard slot and the card you plugged in, talk to each other.
Okay.
They figure out the maximum number of lanes they both support and agree on how many to actually use. So if you put an older by 8 card in a newer by 16 slot, they'll negotiate and run the link at by 8 speed.
Oh, that's clever for compatibility.
Exactly. It ensures things generally work even with mixed generations of hardware. And it also adds a bit of fault tolerance. If, say, one lane in an by 16 link fails, the system might be able to renegotiate and run as in by 15 or maybe even in by 8 link, keeping things working, just slower.
Does the driver need to know about this negotiation?
Well, the negotiation itself is handled by the hardware, but the driver does need to be aware of the actual negotiated link width because that determines the maximum bandwidth available, which can be important for optimizing performance.
And with newer PCIe generations packing more speed into each lane, does that change how systems are designed, how lanes are allocated?
It absolutely does. Since, say, PCI 5.0 can deliver the same total bandwidth with fewer lanes than PCIe 4.0, system designers have more flexibility.
How so?
Well, a device that needed an by 16 slot on PCIe 4.0 might only need an by 8 slot on PCIe 5.0 to get the same performance. That frees up PCIe lanes from the CPU or chipset to connect other high-speed devices.
Right, because the CPU only has a limited number of lanes it can provide directly.
Exactly. So efficient allocation becomes really important. You see things like lane bifurcation, where an by 16 slot can be split into 2 by 8 slots, or even 4 by 4 slots, especially on high-end motherboards, to connect more devices directly to the CPU lanes. Drivers need to be aware of these possible configurations.
You mentioned earlier that PCIe has a layered architecture, kind of like networking models. Why layers?
Yeah.
And what are the important ones?
The layers are key for modularity. It breaks the complex problem down into manageable pieces, like building with Lego bricks. Each layer does a specific job and has clear ways to connect to the layers above and below it.
Okay.
This makes it easier to develop, debug, and evolve the standard over time. You can improve one layer without breaking everything else.
So what are the main layers we should know about?
Okay, starting at the top, you have the application layer. This isn't strictly part of PCI itself, but it's where your actual applications and high-level protocols live, like the NVMe protocol for SSDs or Ethernet protocols. Below that is the transaction layer. This is really the brain of PCIe communication. It handles setting up data transfers between system memory and the device, sending messages like error reports, and it builds and interprets the basic data packets called transaction layer packets or TLPs. It also manages flow control, making sure data isn't sent faster than the receiver can handle and keeps transactions in the right order.
Okay, transaction layer, what's next?
Down from that is the data link layer. Its main job is ensuring reliable, error-free data transfer between two directly connected points on the link. It handles things like acknowledging received packets, ACK-THENIX, checking for errors using something called LCRC, managing link-level flow control using credits, and controlling low-power states for the link.
Got it. And at the bottom?
At the very bottom is the physical layer. This is where the actual electrical signals happen. It's split into two parts. A logical subblock that manages things like link training, state machines, and special synchronization patterns, and an electrical subblock that deals with the nitty-gritty of decoding the signals and physically transmitting them across the wires.
So where do the device drivers fit in? Which layers do they mainly interact with?
Drivers mostly talk to the transaction layer, the data link layer, and the logical part of the physical layer. They're involved in, say, setting up TLPs for data transfers, managing data flow credits, checking link status, and handling logical link states.
But not the raw electrical stuff.
Generally, no. The beauty of the layers is that the driver is abstracted away from the complex electrical signaling details. So when PCIe gets faster with the new generation, which is mostly a physical layer, change the way the driver interacts with the transaction and data link layers usually doesn't change dramatically. That modularity is a huge win for driver development and maintenance.
That makes a lot of sense. So drivers are like translators, bridging the OS and the hardware. What are their core jobs?
Exactly. They're translators. They take high-level commands from the OS or applications like read this block from the SSD or draw this triangle on the screen and translate them into the specific low-level instructions the PCI device hardware actually understands.
And how do they do that?
It involves several technical things. Writing specific values into the device's hardware registers, setting up direct memory access DMA for moving data efficiently, and handling interrupts, which are signals from the device back to the CPU.
Our sources mentioned this often involves kernel mode. What does that mean? Why is it important for drivers?
Right, kernel mode. It's a highly privileged execution level in the operating system. Drivers running in kernel mode have direct, unrestricted access to system hardware memory, CPU instructions, everything. This deep access is necessary for them to control the hardware effectively. But it's also risky. A bug in a kernel mode driver or a security flaw can crash the entire system, corrupt data, you name it. That's why kernel driver development is considered complex and requires a lot of care and rigorous testing.
But the end goal is still to make things easy for regular applications, right?
Absolutely. Even though the driver is doing all this low-level heavy lifting, its job is ultimately to present a clean, standardized interface to applications, usually through the operating system's APIs.
Like read file, write file in Windows.
Exactly, or maybe vendor-specific libraries. Applications use these high-level functions, and the driver underneath handles all the messy hardware details, making the specific device look like any other standard device to the application.
Okay, so when you plug in a new PCIe card, the system magically finds it. How does the OS even know it's there and what it is?
That's the plug-and-play magic, managed by a process called enumeration. When the system boots up or you hot plug a device, the OS or the system firmware like UEFI starts probing the PCIe bus.
Probing, like asking anyone there.
Pretty much. It checks every potential slot and location. Every PCIe device has standard configuration registers right at the beginning. By reading these, the system finds the device's unique vendor ID and device ID. Think of it like a digital name tag.
Okay, vendor and device ID.
Yeah. On Linux, you can use the lpsci command to see all the devices the system found during enumeration. It's a really useful tool.
So once it finds a device and reads its IDs, what happens next?
Then the OS needs to give it resources to work. This means assigning it a unique bus number within the PCIe tree structure, maybe reserving some I/O port addresses, less common now, and crucially, allocating chunks of memory address space for memory mapped I/O or MMIO. These memory regions are defined by the device's base address registers, or bars.
The bars.
Okay. And remember, PCIe is a tree structure. You have the root complex in the CPU, then maybe PCIe bridges branching out to the slots where endpoint devices are connected. Enumeration walks this whole tree, finding and configuring everything. But this whole process relies on link training succeeding at every step of the path. If a link fails to train, devices beyond it just won't be seen.
Then those IDs, vendor ID, device ID, are how the OS figures out which driver to load.
Exactly. The OS takes the vendor ID, the device ID, and also something called the class code, which tells it the general type of device, like network controller or graphics adapter. It uses this combo to look up a driver that says, hey, I know how to handle that specific device. Driver developers have to put these IDs into their driver's metadata, like in a structured device side table in Linux, so the OS can make the match.
Can you quickly recap those key IDs? What do they tell us?
Sure. Vendor ID, VAD. Assigned by the PCI SIG group to the manufacturer, like Intel or NVIDIA. Device ID, DID. Assigned by the manufacturer to a specific chip or product line. Then you often have subsystem vendor ID, SVID, and subsystem device ID, SSID. These identify the company that actually built the add-in card, like Asus or Gigabyte, and the specific model of that card. Finally, the class code, a broader category like display controller, network controller, mass storage controller, etc. Together, they give the OS a pretty complete picture of what it just found.
Okay, OS finds the device, loads the driver. Now, how does the CPU actually talk to the device? Send commands, get data back.
One of the main ways is memory mapped I/O, or MMIO.
M&IO, we mentioned that.
Right. The basic idea is that the device's control registers and sometimes blocks of its own memory are mapped into the CPU's main memory address space.
So the CPU thinks it's just accessing regular RAM.
Kind of, yeah. The CPU uses its standard load and store instructions to read from or write to these specific memory addresses.
And how does that reach the device?
The root complex part of the CPU chipset intercepts accesses going to those special MMIO addresses. It translates them into PCIe packets, the TLPs we mentioned, and sends them over the PCIe link to the device.
Okay, and the device advertises these memory regions through its bars.
Exactly. The base address registers in the device's configuration space tell the system, here are the memory ranges I respond to.
Seems like that simplifies things for the CPU, just one way to access memory in devices.
It does unify access, yeah. No need for separate I/O instructions like in really old systems, but there are catches for driver developers. Caching is a big one.
Caching?
Yeah, the CPU caches memory accesses for speed. Writes to an MMIO address might sit in the cache and not go to the device immediately. Reads might come from the cache instead of the device's current state, so drivers often need to use special instructions, memory barriers, to flush caches and make sure the CPU and device are properly synchronized.
Ah, okay. That's subtle.
And super important, those BAR addresses aren't fixed. The OS assigns them dynamically during enumeration, so the driver must read the bar values after enumeration to know where to talk to its device. Using a wrong or assumed address is a classic driver bug.
MMIO sounds good for control stuff, registers. But what about moving huge amounts of data, like from an SSD? Seems slow if the CPU has to handle every little piece.
You're absolutely right. For bulk data transfer, the go-to method is direct memory access, DMA. This is the high-speed path. Unlike MMIO, where the CPU pushes and pulls every byte, with DMA, the CPU sets things up and then tells the device to handle the transfer directly with system memory.
So the CPU says, okay, device, read 1 gigabytes of data from this spot in RAM and process it, and then the device does it.
Pretty much. The CPU allocates a buffer in RAM, gives the device the memory address of that buffer, tells it how much data to move, and kicks off the transfer. The device then manages the whole thing, moving data directly between its own internal buffers and system RAM without the CPU needing to intervene constantly.
And the CPU is free to do other things.
Exactly. It significantly reduces CPU overhead. The device just signals the CPU when it's done, usually with an interrupt. This asynchronous operation is absolutely crucial for performance, especially with PCIe 5.0 and beyond. Think NVMe SSDs hitting gigabytes per second, AI accelerators crunching data, fast network cards. They need DMA.
What's the driver's role in DMA?
The driver is responsible for setting it all up, allocating the memory buffers, telling the device the physical addresses, handling address translation if needed, managing synchronization, maybe setting up scatter-gather lists if the buffer isn't one contiguous chunk of memory, and crucially, telling the system the device's addressing capability, can it handle 32-bit addresses or 64-bit. Setting the right DMA mask ensures it can reach all of system RAM.
You mentioned interrupts again. How do devices use those to signal the CPU?
Interrupts are the device's way of saying, hey, CPU, pay attention, something happened. It's for asynchronous events, a DMA transfer finished, new network data arrived, an error occurred. It's the device tapping the CPU on the shoulder.
Are there different kinds of interrupts in PCIe?
Yeah, there's been an evolution. Older systems used legacy interrupts. These used dedicated physical pins on the motherboard.
Pins, like wires.
Yep. But they had limits, often only one interrupt per device function. And multiple devices might share the same interrupt line, meaning the CPU had to ask around, was it you, to figure out who actually signaled. That polling adds latency.
Sounds inefficient.
It was. So PCIe introduced Message Signaled Interrupts, MSI.
MSI.
With MSI, the device sends a special message over the PCIe bus itself to signal an interrupt. No dedicated pins needed. The big advantage is that a device can have multiple distinct MSI messages, often assigned exclusively to it. This gets rid of the sharing and polling problem, reducing latency. The main limitation was usually a cap of 32 interrupts.
So MSI was better, but maybe not enough interrupts for complex devices.
Right, which led to MSIX. It's an extension allowing for many more interrupts, potentially up to 2048, and each one can be configured independently, even targeted at specific CPU cores for better load balancing. If a device supports MSIX, that's usually the preferred way to go.
So the move to MSIMZX was really about performance and avoiding those old legacy interrupt issues.
Definitely. Handling interrupts efficiently is critical for high-speed PCIe devices. Modern drivers use OS functions to allocate and manage these MSIMZX vectors.
What if a driver does have to deal with those old shared legacy interrupts? Any special considerations?
Yes, absolutely. If an ISR, the interrupt service routine in the driver, gets called for a shared legacy interrupt, the very first thing it must do is check its own device's status registers to see if it was the one that actually generated the interrupt.
Why?
Because if it wasn't its device, it needs to quickly say, nope, not me, and return so the OS can call the next driver sharing that line. If it doesn't check, it might process a phantom interrupt or prevent the real driver from handling it promptly.
Okay, check first. Anything else?
Yeah, power state. Before reading any registers from the device, especially interrupt status registers, the driver should check if the device is actually powered up and in an active state. Reading from a device that's asleep or powered down can return garbage data and lead to all sorts of weird behavior.
Good tips.
Yeah.
Now, we keep mentioning the configuration space. Can you elaborate on that? What's in there? Why is it so central?
Right, the configuration space. Think of it as the device's built-in control panel and ID card all rolled into one. Every PCIe device has a standardized block of registers. The first 256 bytes are standard, containing things like the vendor ID, device ID, class code, status and command registers, and importantly, the bar.
The base address registers,
Yeah,
yeah.
exactly. There can also be an extended configuration space up to 4KB for more device-specific stuff. Drivers and diagnostic tools need to read and write this space to configure the device and check its status. The OS provides APIs for this.
So it's where the OS learns about the device and tells it how to behave.
Precisely. It's the main gateway. The OS reads the IDs here, writes to the BRs to assign memory DOSes, enables features using the command register. Understanding the config space layout is fundamental for a PCIe driver developer. They use OS functions to read and write bytes, words, 16 bits, or double words, 32 bits, in this space all the time. Getting config space settings wrong is a very common source of driver problems.
And you mentioned resizable BR before.
Yeah.
That uses the config space too.
Yep. Resizable BARR, or Smart Access Memory, as some call it, is a feature where a device, typically a GPU, can negotiate with the system to get a much larger BRR mapping than usual. This negotiation happens using specific bits and fields within the PCIe configuration space registers. Allowing the CPU direct access to more, or even all, of the GPU's memory can boost performance in certain games and applications. It's a good example of how the config space enables newer features.
This all sounds pretty involved. If someone listening wanted to actually try developing a PCI driver, what does the setup look like? What should they be prepared for?
Okay, for Linux, you typically need the kernel source code for your target version, the development headers, and build tools like GCC. You might need a cross-compiler if you're building for a different architecture like ARM, and the ELT-BY utility is your best friend for seeing what's on the bus.
And for Windows?
For Windows, you'd use Microsoft's Visual Studio, plus the Windows Driver Kit, WDK. The WDK has all the specific headers, libraries, and tools for building Windows drivers. And be aware of the HLK Hardware Lab Kit certification process, which is often required for commercial Windows drivers to ensure stability and compatibility.
And we talked about the challenges of kernel mode. Are there easier ways to start?
Kernel mode is complex, and mistakes can crash your system. So yeah, there are some tools that try to simplify things. For instance, Django WinDriver provides an API that lets you write much of your driver logic in user mode, but it handles the tricky kernel-level stuff like DMA and interrupts for you, aiming for near kernel performance without all the kernel mode risk. But regardless of the tools, the key takeaway is testing, testing, testing. Unit tests, integration tests, stress tests, regression tests, especially for drivers because bugs can have serious consequences. Automated testing is highly recommended, almost essential for commercial products.
So what's the basic code structure? For a Linux driver, what are the essential pieces?
In Linux, you typically start by registering your driver with the kernel's PCI subsystem using cRegister driver. You pass it a struct driver structure.
Okay.
That structure mainly contains pointers to callback functions. The two most vital ones are probe and remove. It also contains that IDSatable we talked about, which lists the vendor and device IDs your driver supports.
Probe and remove, what do they do?
The kernel calls your probe function when it finds a device whose IDs match an entry in your IDSatable. This is your setup routine. Inside probe, you do all the initialization, enable the device, request memory regions, MMIO bars, maybe request IO ports, set up DMA, register your interrupt handler, basically bring the device online.
Got it. And remove.
Remove is the opposite. The kernel calls it when the device is being removed, maybe the driver is unloaded, or it's a hot plug device being unplugged. Your remove function has to clean everything up, unregister the interrupt handler, release the memory regions and IO ports, disable DMA, disable the device, put everything back the way you found it, essentially.
So the kernel handles finding the device using the ID cable and just tells your driver, here's a device for you via probe, or this device is going away via remove.
Exactly. It's an event-driven model. The driver just needs to react to those events. And meticulous resource management in probe and remove is absolutely critical. Forgetting to release a resource in remove leads to leaks, which can destabilize the whole system over time.
Okay, inside that crucial probe function, what's the typical sequence of steps to get the device working? Is there an order?
Yes, there's a definite, generally recommended order. And getting it wrong can cause problems. First, you enable the PCI device using signable device. Super important first step, and always check if it succeeded.
Okay, enable first.
Then, if you need DMA, you enable bus mastering using Siddhartha Master. After that, you request the resources, the MMIO regions defined by the BERS, and any I/O ports using functions like subrequest regions. Critically, use the resource addresses the kernel gives you in the SysDet structure. Don't just grab them from config space yourself.
Right. Let the OS manage resources.
Exactly. Next, if you're doing DMA, especially on a 64-bit capable device, you need to set the DMA mask using DMAset mask and maybe DMAset coherent mask. This tells the kernel how many address bits your device can handle, ensuring it can reach all of system RAM if needed.
Okay.
And finally, you register your interrupt handler using a requester, or if using MSIMZX, you typically allocate the interrupt vectors first with Sakailo's surf vectors, and then register a handler for each vector with requester.
So enable device, set master, request region, set DMA mask, request IRQ. That sequence is key.
That's the general flow, yes. Sticking to that order helps avoid many common initialization pitfalls. And always remember, you're requesting resources from the OS, the central manager. If a request fails, handle it gracefully, don't just crash. Resource conflicts are usually OS issues, but your driver needs to be robust.
Driver development definitely sounds challenging. What are some common roadblocks or specific PCIe issues developers run into? Any debugging tips?
Yeah, it's challenging. General hurdles include just understanding the hardware deeply, handling platform variations, power management, security concerns, and the pain of kernel debugging limited tools, risk of crashing the machine you're debugging on. Testing is also hard. You need the actual hardware, maybe multiple versions.
Okay, but specifically for PCIe, what goes wrong there?
PCIe-specific issues. Well, enumeration failures are common. The device just doesn't show up. Often it's a problem with link training. The electrical handshake fails, maybe times out. It has about 100 meters after power good.
Link training again.
Yep. Then there are DMA problems. Data corruption, missing data. Could be you requested a transfer size bigger than the device's max payload size allows, or maybe issues with low-level flow control signals. Another category is unsupported requests or completion timeouts. These often point to bad BR configuration. The CPU tries to access a BR that isn't set up correctly, or maybe the device is out of memory. Seeing a virtual bar in ELF-SPI can mean the link dropped unexpectedly. A disabled bar usually means the memory enable bit isn't set in the command register.
Subtle things.
Very. You might also see receiver overflow errors, sometimes hinted at by AER stats in ELF-SPI. This could mean flow control credits weren't managed properly, or maybe the relaxed ordering bit wasn't set correctly for certain transaction types. The point is, debugging often requires looking at the whole picture: software, configuration, link state, even physical layer integrity.
So it's not just software debugging.
Often not. You might need hardware tools, oscilloscopes, protocol analyzers, BERTs, to really diagnose tricky issues. And that's why PCIe compliance testing through the PCI SIG is so important for commercial devices. It validates interoperability and catches many potential problems early. Doing pre-compliance testing during development is a very good idea.
Wow. Okay, this has been incredibly insightful, a real deep dive. Can you maybe summarize the absolute key takeaways for everyone listening?
Sure. We've seen that PCIe is the essential high-speed serial backbone of modern computers. It replaced older parallel buses with a switched point-to-point architecture using scalable lanes by 1, by 4, by 16, etc.
Right, faster and more efficient.
Exactly. Each generation roughly doubles the speed per lane while keeping backward compatibility. We looked at the layered architecture transaction, data link, physical, and how drivers mainly interact with the upper layers abstracted from the electrical details. We covered key driver tasks: enumeration, finding the device via VDID class code, communication via MMIO, using bars, and high-speed DMA, handling events with interrupts, legacy versus MSIMZX, and the critical role of the configuration space for setup.
And the challenges, like kernel mode, resource management, and debugging those tricky hardware-software interactions.
Precisely. It's a complex but vital technology.
And it's clear its importance is only growing, right?
Mm-hmm.
With AI, faster networks, bigger data.
Absolutely. The demand for bandwidth isn't slowing down. PCI's continued evolution is fundamental to enabling the next generation of computing performance across the board.
If listeners want to learn even more, where should they look?
Well, the official PCI SIG specifications are the ultimate reference, though very dense. For driver development, the Linux kernel documentation and Microsoft's WDK documentation are essential. Hardware vendor websites often have great white papers and application notes. And don't forget online developer communities and forums, lots of practical knowledge there.
Excellent resources. Okay, finally, a thought for you, our listener, to take away. As PCIe bandwidth keeps exploding, think about how that impacts future systems. Go beyond just faster games or file copies. What entirely new applications, new kinds of hardware might become possible because devices can exchange data that fast. Maybe digging into the latest PCIe spec or even trying to write a simple driver for a device that interests you could be a fascinating next step on your own tech journey.